Okay, I want to talk about transets. These are a generalization of the usual set theories and talk about it as a way of totalizing the whole of mathematics. So I've described this scenario before. We have real arithmetic is partial because we can't divide by zero. We give ourselves the ability to divide by zero, so we've totalized the division operator. That's fine, but we still have sentences of arithmetic which we can't solve. So I can ask for the number which is greater and less than zero. And there is no such number in Transreal arithmetic, so again we fail and the arithmetic is partial. Well, we can fix that by asking for the set of numbers which are greater and less than zero. There are no such numbers, so we get the empty set. That's fine. But then we run into the paradoxes of set theory, the Russell set, which turns out not to be a set, it's a proper class. And so we would like a way of being able to describe anything as some kind of a set. And that's what transets are going to provide for us. So I'm going to give a framework for totalizing the whole of mathematics. The framework is quite straightforward. So the agenda, I'm going to talk about transets. Now, many years ago, Walter asked which set is nullity, and I've never been able to answer that question. I've never been able to find a set in set theory which is a natural model of nullity. But I can tell you which transet is nullity, and we'll see that later in the talk. And all of this we can do with just having the structure of transets. Later on, I will present the operators of transet theory so that we have an entire set theory at our disposal. I haven't explored that set theory. Today is just a statement of work in progress. This is how far I've got so far. So a transet is a metastructure implemented in the base set theory. Take your favorite set theory. It constructs sets with a constructor, maybe like this one, the set x such that phi of x. So every x is a member of the set providing phi of x, some sentence in your base logic, is true. If we've got a constructor like that, then we say that the tuple x phi of x is a transet element. So a transet element relates a variable x to its truth value. And then we say a transet is a set of these things. So it's a set of these tuples. And notice the condition there. It says this tuple is a member of the transet if true. Well, if true is always the case, so every tuple is a member of the set. And we could add that as an axiom to a set theory. We could say for all x, this set exists. Now that is an exceedingly strong axiom, that transet can be a proper set, depends on what x is, proper class, and so far as I can see, it could be the class of all classes. If the variables x are continuous, not discrete, then it could be larger than the class of all classes. If anyone wants to know about continuous variables, I'll answer that in a question. So, when phi of x does not evaluate to any of true t and false f, it's said to evaluate to a gap g. And in this case, the transet element, the tuple x phi of x, doesn't exist. And x is said to lie in the background of the transet. So what sort of things are in the background? Well, they're all the things we don't know about. They're all the things that we haven't started to analyze yet. In addition, they may be things where we do know what x is. We've got some sentence of arithmetic, but we can't evaluate it. It's undecidable. sentences. And all of those things go into the background. Now, if we know the sentence for X, we could have a transet element, which is the sentence. So you can have the sentence X, the truth value of that sentence is true, it really is a sentence, but you don't know how it evaluates. And that lets us describe gaps, the stuff in the background, the stuff we don't know how to deal with. A bit of vocabulary, which will be useful later, is that everything that's not in the background is in the foreground. And the foreground usually is where the action is in a mathematical proof. When phi of x evaluates to the single truth value true, t, it's said to evaluate to just true, t. And notice that I've used the same symbol t for both true and just true. This is deliberate. T is a context-sensitive element. If t occurs on its own, it's true. Sorry. If t occurs on its own, it's just true. If t occurs together with f, it's true. So we're distinguishing the context of t. In this case, the single transet element x of t exists, and x is said to lie inside the transet. So being inside a transet is exactly the same thing as being inside a set. Conversely, when phi of x evaluates to single truth value false, f, it's said to evaluate to just false, f. Again, f is context sensitive. If it's on its own, it's just false. If it occurs in combination with t, then it's false. In this case, the single transet element xf exists, and x is said to lie outside the transet. So being outside of a transet is exactly the same thing as being outside of a set. When phi of x evaluates to both true and false, it's said to evaluate to a contradiction, C. In this case, that both transets exist, x of t and x of f, and they're said to lie on the border of the transet. Now I chose the word border distinct from boundary because I don't want to make any claims about the topology of the sets that we're considering. So border is a new word, and its purpose is to be potentially something different from a boundary. Now, a transet with an empty border is a set because we have only an inside and an outside. Yes, we have some stuff in the background, but that's always true. If you've got a set in set theory, then there are lots of things in the world that are not in your set. They're notionally part of a background. An interesting case is where the transet has a non-empty border, and then we call the transet an antinomy. And when I first introduced transets at the first conference in Brazil, I explicitly dealt with antinomies as a first-class object. So we had sets and antinomies. And we can now do all, and that was a way of disposing of Russell's paradox. We can now do all of that just using transets. Right, so transets have four parts: a background, an inside, an outside, and a border. And we can prove that those four parts are necessary. So let's take as axioms x, not y, z, not z. Now w is in the background. Why is w in the background? Because we haven't got any axioms that relate to it. We don't know what it is. It's something that potentially will make sense in the future. We can't evaluate w to a truth value. X is inside because it's true, y is outside because it's false, and z is on the border because it's true and false. And notice that we have considered all four combinations of the two symbols true and false. So we have... Right, this starts to get interesting. Gödel's incompleteness theorems tell us that about if a about things that are complete. So complete means that all true statements are provable. And one of the theorems says that if a logic is complete, then it's inconsistent. And most mathematicians take that to mean that we can't have a complete system. But since the invention of paraconsistent logics which allow contradictions, we're quite happy with that statement. So we can have a complete system of paraconsistent logic. It's inconsistent as required by Gödel, and that's fine. Paraconsistent logics know how to deal with inconsistencies. Second consequence is that we can get the same result with transets. We can use a consistent logic that is applied only to the transet elements, and that can be complete. Then the contradiction is restricted to the transet elements. We're completely happy with contradictory transet elements. Now, I don't have any logic to offer you, but I'm just saying it is possible, it's conceivable, that there is a paraconsistent logic that is complete. It's possible that there is a consistent logic applied to transet elements that is complete. And it's possible in the latter case that it's a logic that we already know and use. Right, some more consequences that are more to do with transreal arithmetic. The usual set theoretical construction of multiplication of cardinals makes the product of 0 and any cardinal 0. So in essence, 0 times any cardinal is 0. And that's fine for the usual arithmetic. It's not fine for transreal arithmetic because we have 0 times infinity equals nullity. We want a different result. So infinity cannot be, say, the cardinal of the universal set if we're working with a set theory that has a universal set. So we need to do something else about it, and there are two things we can do. First of all, we can take transreal infinity and nullity as meta-objects, objects built from set theory by taking the trans-Dedekind cuts. So work that Thiago and I did showed that if you take the definition of Dedekind cuts, you notice that Dedekind excluded 3 cases, and those 3 cases correspond to transreal plus infinity, minus infinity, and nullity. You have to slightly change the way the Dedekind operators work to account for the existence of more symmetry. Another way you can resolve this problem is to say that infinity is an ordinal. Now, ordinal numbers obey their own arithmetic, which is different from cardinal arithmetic. So you've already removed the infinity from the problem that 0 times infinity equals nullity, or 0 times a large cardinal equals 0. In addition to that, you want to take nullity as an ordinal with cardinality 0. Of course, nullity is unordered, as always, but we'll give it the status of an ordinal or a transordinal if you prefer. And it has cardinality 0. We don't know what the contents are. The reason we insist on cardinality 0 is that if it was any other number, then there could be we could build a set that corresponds to it, and I've never found any way of doing that. So this is a suggestion that a way of escaping the problem that cardinal times 0 equals 0 is to say that transreal infinity is an ordinal with cardinality the universal set, and nullity is an ordinal with cardinality 0. I don't want to say any more about that possibility because I'm just about to explore the trans-Dedekind cuts. So to answer Walter's question, what set is nullity, I can't do that. I can give you the transet that is nullity. So let's take all and only the real numbers in the foreground and call this a real transet. So the inside, outside and border contain all and only the real numbers. Everything else is in the background. And that's the way that you restrict a transet to work over a chosen domain, here the domain of real numbers. Now we identify the inside of a real transet with the left Dedekind cut. If it contains all reals, the whole cut is Transreal positive infinity. And that's a result from the paper that Thiago and I published. We identify the outside of a real transet with the right Dedekind cut. If it contains all reals, the whole cut is Transreal negative infinity. As a consequence, nullity is the real transet with all reals on its borders. So now I can tell you what nullity is. Transreal nullity is the real antinomy. So you have an answer, Walter, albeit not in set theory. Right, that much was done with just the structure of transets, having elements, having a set of elements. But we would like to produce an actual set theory that has connectives, intersection, complement, and so on. So I'm going to adopt a functionally complete set of logical connectives using a four-valued logic with the values gap, just true, just false, and contradiction. Because the set is functionally complete, we can immediately write down all the connectives of set theory. We just take their definition as logic, apply the four-valued definitions, and hey presto, we have a set theory. I'm not going to commit to any proof methods at the moment, simply because I haven't explored them, but I will say something about proof methods in the remaining slides. Right, here is a four-valued negation. So on the top row we have true, false, contradiction, and gap. If we apply the usual negation operator to true, we get false. If we apply the usual negation operator to false, we get true. Contradiction is not a truth value. Contradiction is the co-occurrence of true and false. If we negate true, we get false. If we negate false, we get true. We've now got true and false, which happens to be a contradiction. A gap is not a truth value. A gap is the absence of truth and falsehood. If we apply the usual negation operator to nothing, we have an arity error. We were expecting to apply not to one object, there's no object there, that's an error. And we define that in the case of that error, we produce no result. The absence of a result happens to be a gap. So we write down that the negation of a gap is a gap. Notice that the first two elements are Boolean logic. The first three elements are a paraconsistent logic. It's one of the well-known paraconsistent logics. I forget which one, I'll have to look it up. And with gap present, it's a totalized paraconsistent logic. Things get more interesting when we look at binary operators. So as usual, the top left 2 by 2 block is Boolean logic. Let's look at the first row, third column. We've got true and contradiction. Contradiction is not a truth value, it's the co-occurrence of true and false. True and true is true, true and false is false. We now have true and false as results, and that happens to be a contradiction. When we take true with gap, then we have an arity error. We've got true as an argument. There's no argument in the gap, so our AND operator fails, produces no result, and no result happens to be a gap. So gap is absorptive everywhere in the last row and column. So now we have the top left 2 by 2 block is Boolean logic. The top left 3 by 3 block is a pre-existing, recognized, well-known, but I've forgotten its name, paraconsistent logic. And now we've totalized it by adding a bottom element, an absorptive element. In a paper which Jan gave me a copy, he says that there are four functionally complete four-valued logics. So I guess this is one of them. In that paper, Jan uses one of the logics. I haven't checked to see if this is the logic he uses. Now let's just explore this idea of multi-valued logics. If you have a zeroed valued logic, you can't say anything about the universe. You can't use it. There is no use to a zero valued logic. Let's consider all the combinations of a zero valued logic. There are 2 to the n of these with n equal to 0. 2 to the power 0 equals 1. So we have one truth value. Call it observation if you like. We can use observation. We can observe the universe, but we can't distinguish anything within the universe. So a one-valued logic is of no practical utility to us. Well, let's consider all the combinations of a one-valued logic. There's 2 to the power 1 equals 2 of those. That gives us Boolean logic, and suddenly we can make distinctions in the world. We can say that an observation has occurred, true, or it hasn't occurred, false. As we know, if you consider multiple statements about something, they can be contradictory or a gap. And so we would like to consider those cases. If we do that, there are 2 to the power 2 equals 4 cases to consider. Notice that if we have a total system with 2 to the power n states, then the answer is never 3. You can never have a 3-valued total logic. So if you use a 3-valued logic, you are guaranteed to produce a partial system. The Boolean 2-valued logic is total. The problem arises when you consider multiple statements of that logic. If we want to consider multiple statements, we run the risk of having contradictions and gaps. So we are driven to step up from 2 to 4 values. We cannot have that contradiction and gap are symbols. If we did, we could have contradictions of contradictions and gaps of contradictions, and we'd have to step up to an 8-valued logic and then 16 and so on forever. So if we want to produce a total system of logic, the smallest possible one is a 4-valued logic. If it's to be functionally complete, then Jan tells us there are 4 possible logics to choose from, which is quite an interesting result. OR is just the same as before. The top left 2x2 block is Boolean, the top left 3x3 block is this paraconsistent logic, I've forgotten what it's called, and the last row and column is a parity error, which becomes our absorptive element gap. So, having told you what a transet element is, having told you that a transet is a set of transet elements, and having now given you a paraconsistent logic, which is functionally complete, and I've checked that, then you can write down all the operators of set theory. What I haven't done is give you any proof methods. Now, I do want to say something about proof methods. So, of course, many people have discussed multi-valued logics. And for example, in the step up from 2x2 Boolean to 3-valued logics, people tend to be conservative. So they say it might be true or it might be just true, and I will write operators, inferences, which are agnostic as to which of those 2 cases is the case. That produces logics which are conservative, which are monotonic but which are weak. And we don't have to be monotonic. We can say, we know it's just true and just false, so we'll be Boolean and use all the power of Boolean logic. We know that it is true and false, a case of a three-valued logic where we have to be weak, but we can be stronger than is usually the case because we know it is actually the case that we are dealing with something that is true or else just true, false or else just false. That, of course, produces a non-monotonic logic. But that is, in fact, what the history of mathematics is. The history of mathematics is non-monotonic. You think certain theorems are true, somebody proves that they're not true, and you adjust your beliefs. The reason people don't like non-monotonic logics is they are very costly when you have to backtrack. So if you discover that something you thought was true, the whole of mathematics can be expressed as a set. You find it can't be, oh my God, you've got a lot of work to do. But so far as I see, we have to admit these non-monotonic logics to capture all of the expressive power of the history of mathematics. So my preference is to go down that route of distinguishing true from just true and false from just false. Other people might take a different route. So in conclusion, transets totalize sets and hence totalize the whole of mathematics. Of course, this is just a framework. I haven't actually gone around and totalized the whole of mathematics. I'd have to live for 1 billion years to do that. Walter, you finally have an answer. Transreal nullity is the real antinomy. It does still nag me that I haven't answered which set is nullity, and I will continue to think about that, but for the time being, this is the best answer you're going to get. Many transset theories are possible. Jan has said there are 4 total functionally complete logics. We could use a bigger logic. You could use an 8-valued, you could use a very many-valued logic, do fuzzy logic. There was all sorts of things you could do. I've set out one foundation for a transset theory, and there are many ways that you could develop from that foundation. Okay, that's it. That's what I wanted to say. I will add that I am drinking apple juice, not beer. Right. Any questions, anybody?
James, what do you mean exactly by many set theories are possible, many transset theories are possible? Could you give some examples?
Yeah. So in set theory, you have the union operator, and you say if X is a member of the set and Y is a member of the set, then it's a member of the union. So you're using a logical operator and to combine elements of the set. I've given you a 4-valued logic. There are 4 other functionally complete ones. So you could, if you use a different logic, you'll get a different set theory. The advantage of using a functionally complete logic is huge. You write down a functionally complete subset, for example, not and or not or, and then you can mechanically translate all of the definitions of all of the operators of set theory into your new set theory. So that's why functional completeness is useful. If you're not functionally complete, then you're forced to make decisions about how you're going to do it. So the reason that you get many different set theories is you could choose any of 4 functionally complete truth tables, and those would give you 4 different set theories in a family. And the other way you can get multiple set theories is by having different proof methods. So there are many set theories at present, and they differ in how they set out proofs. Is that clear?
Good.
Good. You've got your microphone off.
Yeah. Suppose you would start out with a set theory which only contains finite sets.
Yes.
Would you then be able to produce a sort of simplified trans set theory on top of that?
Yes.
Okay.
And the answer is very straightforward. You take the elements of your finite set theory, that's an alphabet of sets. All sets can be represented exactly as transets. You look at what's inside, what's outside, job done. And all we are doing is adding the truth values to the predicate. So we're saying this element is inside or outside, and we allow the possibilities that it's contradictory or gap.
But would we get any antinomies in that world?
Yes, you could, and I gave an example of that with my axioms of Z and not Z.
Okay, that works in a finite world.
Yeah.
So the Z and the not Z would be finite sets, for instance.
They could be finite sets. They could be number 1.
Right.
Create havoc with the number 0.
That kind of structure would, of course, be much simpler than a full-fledged set theory.
Yes, it would.
And it would be helpful in organizing the whole story.
Mm.
Yeah.
What I particularly like about transets is the link to Dedekind cuts. So the transreals are generated by the Dedekind cuts. The Dedekind cuts correspond to transets. So there's something deep about the structure of transets that is reflecting Dedekind cuts and hence reflecting the transreals. So you can say with some honesty that transets are a better basis for the transreals than sets are. A more natural basis.
James, I find the talk extremely interesting. It goes way over my head, I have to say, but I can, and as with Jan's work, I can grasp little bits of it and fit it into my world. When we have I would actually like to tell you a little bit about what I've been doing lately when we get to our workshop part. This concept of distinguishing inside from outside is very much part of my thinking about all kinds of issues, and I'm therefore intrigued by this idea that you formalized, and something I have to learn more about.
Well, if there are no more questions, I suggest we move straight to the workshop.